Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, we are going to look at some applications of the exponential functions. Usually, all these problems are involved with growth and decay, as we will see. But before we start, let's write down the form of that function. Usually, this function would look something like that. So if function y of t or something, let's say y of t or y of x, would equal a constant a times another constant b raised to a power, let's say t here since we use t, but could be any variable, t for time usually. Sometimes you see this as a sub n equals a sub 1 times b to the x or something. They are the same thing. The a sub n here, or the y sub t, is the final value of the money you are calculating or the number of some kind of bacteria or something. A sub 1 is the initial value. B here is either growth or decay. We'll talk about that. And X or T here is the number of periods. Okay, so when we are going to make it clearer as we go, so let's look at some examples of questions that are similar to your Regents exam. You will see something similar to that. So the first question, a multiple choice, it says the following function models the value of a diamond ring in dollars. T years, so T here is number of years after it's purchased. It says V of T or Y of T equals something times growth or decay raised to the power of T. And they ask you, what was the original price of the ring? Original meaning initial. Initial is this guy, which is the 500. So I bought the ring for $500. And then later it will uh, being appreciated. Okay, Mike uses the equation B equals 1300 times 2.65 raised to the power of x to determine the growth of bacteria in a laboratory setting. The exponent x here represents what? Well, it's a number of periods. So, total number of bacteria? No, the total number of bacteria would be the B. Percent at which the bacteria are growing? No, the percent would be this guy. That's the growth or decay. Initial amount of bacteria? No, the initial amount is 1300. So definitely is the number of time periods. Yes, number of periods is X. So once you see that, you're just identifying what each part means. Some banks charge a fee on savings account that are left inactive for an extended period of time. So you deposit money in your savings account, but you just forget about it. So they say, okay, if you are not going to use your account, we are going to use this equation uh, we'll see what it means in a second. Okay, what is the y-intercept of this equation and what does it represent? The y-intercept, we understand that the y-intercept always, so if we write b equals, I'm sorry, y equals 5,000 times 0.98 to the x. The y-intercept in any equation is usually when you set x equal to 0. So when I set x equals to 0, I get 5,000 times 0.98 to the 0th power. We know that any number raised to the 0th power is 1, so I get $5,000. And what is the $5,000? initial value. So is it, so they tell you what is the y-intercept? Is the y-intercept 0.98? No, absolutely not. 0.98 again, so it's 5,000, but which one of them? The amount of money in the account initially? Initial? Yes, it is. Or is it the amount after X years? No, the amount after X years would be Y, not 5,000. So it's number three again. Here I will stop and show you the difference between question number one and question number three. Both of them were talking about the initial value, but that's not what I mean. I mean the quantities, the quantity between parentheses. In the first one, it was 1.08, which I can write as 1 plus 0.08, which I can write 1 plus 8 over 100, which I can write as 1 plus 8%. That, since this number altogether is greater than 1, it means 1 is the initial value, excuse me, and the extra is the amount of increase per year. It's not the amount, I'm sorry, it's the percent increase per year. So this is a growth. When we look at number 3, it says 5,000 times 0.98. It's less than 1, so it is absolutely a decay. Because I can write it as 1 minus 0.02. I can write it 1 minus 2 over 100. I can write it as 1 minus 2%. So this one is 8% growth. This one is 2% decay. And now that it makes sense, the bank is penalizing you 2% on the amount you have in your account, 2% for not using the account. Okay, they are just servicing it and you are not making any use of it. So you say, okay, we have to charge you for the service since you are not making any deposits or any movement of your money, but we are doing work to send you, statements and do this and that for no reason. So we are going to take 2% of whatever is in the account to compensate for our work. Okay? So now we understand the growth and decay. Number 4, the value of a home in Buffalo can be modeled by the function. Is that increase, growth or decay? Greater than 1, then it is growth. Okay, where V of t is the value of the house after t years. Yeah, you see that, the final. You bought it for 96,949. What is the percent of increase in the value? Be careful. Percent of increase, meaning percent of growth. So I want to write it something like that. I'm going to say, okay, it's 1.0448, which is 1 plus 0.0448. I multiply by 100 by moving the decimal place 2 units to the right and say this is 4.48 over 100. You see what I did here? I multiplied by 100 and then divided by 100. Multiplied by 100 and divided by 100. So I don't change the value. So this becomes 1 plus 4.48%. That's the amount of growth. So when they tell you what is the percent of increase or growth in the value, it's none of those. It's the last one. It's 4.48. Okay? So this is number 4. Let's move to number 5. The function v of t equals 1350 times 1.017 to the t. I know right away, this is the initial value, this is the number of periods, this is the 0.017. When I multiply it by 100, it becomes 1.7. That's the amount, or that's the growth rate. They ask you the yearly rate of appreciation. Appreciation is another word for growth. Decay would be called depreciation. It depreciates, meaning its value gets smaller. Of this comic book, what is the percent? Notice, again, You subtract the 1, you multiply by 100 by moving the decimal place 2 units to the right, it becomes 1.7. So it's 1.7%, which is number 2. See, very easy, these types of problems, because these are just multiple questions. Then we are going to take a couple of problems and create this function and solve it. The equation A equals that, very similar, is being used to calculate the amount of money in a savings account. What does the 1.02 represent? Well, again, that's growth. If you subtract 1, you get 0.02. You multiply by 100%, you get 2. 2% growth. So is it 0.02% decay, 0.02% growth, 2% decay, 2% growth? Definitely it's 2% growth. It's more than 1. And when I multiply it by 100, I get 2, meaning 2%. A population of bacteria can be modeled by this function where t represents the time since the population started decaying and f of t represents the population of the remaining bacteria at time t, because that's decay. The number of bacteria luckily decreases. So the initial would be higher than the final. You see that? It's the opposite of the growth when the final would be greater than the initial. But here, hopefully, we are taking some medication or something, so the number of bacteria decreases. So I expect f of t to be less than 1,000. Hopefully, right? Okay, so we say, what is the rate of decay of this population? Notice, rate of decay, I have 0.98. We already solved 0.98. I say this is 1 minus 0.02, meaning 1 minus 2%. So it's 2%, one of the answers. That's the rate of decay. Um, okay, so what do we want after that? Jim uses the equation A equals P. Usually, A is the amount in an account. P is the principal or the initial, same as that. Okay, we just use different letters, but A equals P. Well, when we wrote it here, P times 1 plus or minus the rate of decay, if we call it alpha or something, raised to the number of time units. Okay, so investment P after T years for this equation. Which phrase describes the yearly rate of change? Rate of change. They didn't tell you growth or decay, but of course it is growth here because it's 1 plus something. They already wrote it like that instead of saying 1.05. So I just get rid of the 1, multiply by 100, meaning moving the decimal point 2 places to the right, percent. So it's 5%. 5%, and it's more than 1, so it's growth, increasing by 5%. There are more problems, but I think they are all similar. And I think by now you should have mastered this. So let's move to a couple of problems then. In this problem says Mark bought a new laptop for $12.50 at time 0. Okay? At time 0. And you have to get used to that. Time 0 meaning now. Because here it says value in dollars years after the purchase. So I can add another row here that says year 0, it was $12.50. Okay? Now, he kept track of the value of the laptop over the next 3 years as shown in the table below. Which function can be used to determine the value of the laptop for X years after the purchase? Here you have to be very careful because in some we know we are solving exponential, so we know that this is exponential decay because the value was 1250, it was depreciated to 1,000, then 800. Sometimes it's depreciated linearly, not exponentially. So how do I know? If this was 1200, then 1000, then 800, then 600, I see that it decreases 200 per year. Huh, that's the slope of a straight line going down. So it's not exponential. Well, it is exponential, but the power is zero, or the power would be one, meaning it's decreasing at the same rate. But here, in order to know the percent growth or decay, I have to divide either time one value by time zero, or time two by time one, or time three by time two, preferably all of them, to see if the percent is the same. Because if it's not, I don't know, it's not exponential. So when we do that, we see that I can see that from 1 and 2, it's zero point 0.8, right? The multiplier is zero point 0.8. But let's do it. 1000 divided by 1250, it's zero point 0.8. I know that 8 times 8 is 64, so 640 over 800 is also zero point 0.8. And of course, 800 over 1000 is zero point 0.8. So since this zero point 0.8, remember, for example, a sub n equals a sub 1 times b to the x. So here b, which we can write as 1 plus or minus some quantity, I call it alpha. If it's plus, then the alpha is the percent growth. If it's negative, it's percent decay. So now, where is the other paper we were writing on? Oh my God. Just to show you what I mean, because it's the same thing. So here the quantity between parentheses is zero point 0.8. Notice I never write it like that. I have to write it 1 plus or minus something. Of course, here, because it's less, I have to subtract. What do I subtract? I say 1 minus zero point 0.8 is zero point 0.2. And zero point 0.2, when I multiply it by 100, it becomes 20. If I multiply by 10, it's 2. By 100 is 20 over 100, or 1 minus 20%. So now, well, we didn't need to do any of that. In fact, we know that the b is 0.8. So it has to be either 2 or 4. I'm sorry, I thought they wanted us to calculate the percent decay or growth or decay. But here, they already give me, or I calculated zero point 0.8, so I know it's decay, and that has to be either this or that. Notice the quantity outside is the initial value. Many students erroneously pick the 1000 because it's the first value in the table. It must be the initial. No, the initial has to go with time 0. 0 is the present time. Notice this is years after the purchase. So if you use the 1000, that's the value of the laptop a year after you bought it, not when you bought it. Okay, when you bought it as a new, it was 1250, so the answer is 4, but many would pick 3. Okay, Jill invests 400 in a savings bond. The value of the bond in hundreds of dollars after X years is illustrated here. So now they gave me the original value. Okay, so I know, and all of them starts with 4, so all of them I can decide. Now, this is appreciation, so it couldn't be 1 or 2 because the values are increasing. What I need to do is to divide 5.4 by 4, year 1 by year 0, I get 135. Make sure here, of course, I know it has to be exponential, but if it's a regular problem in the test, I don't know, they don't tell you on the top, oh, this question is exponential, right? I have to divide this by 5.4 and I get the same value. So I can do even the third one. Usually, sometimes they approximate. So you may get 1.348 for it, or 1.352 or 1. So be careful. Don't just say, no, it's not the same value. You see? 1.3497. That was 1.35, but they were rounding it to two decimal places, okay? Because um, so just to approximate, so that means they are the same value. Don't say, oh, that's not exactly 1.35. Yeah, because you cannot get exactly 7.291 or 2, yeah, 0.2913 or whatever, or 9.8423. And then you say, okay, I don't have that fraction of a penny, so round it, right? Be careful. Uh, Of course, it's a growth because it's greater than one. It cannot be a decay. So that's a trick. You may see this number and say, oh, that's what I got. And no, it's number three, not three and four. The last one says Mike knows that three and six and a half, four and 17.55 are points on the graph of an exponential function. And he wants to find another point on the graph, meaning five and something. So yeah, three and six and a half, four and that, and then he needs five. So he said, okay, the difference between six and a half and 1715 is 11.05. So I'm going to add 11.05 here to get 28.6. Is he correct? Absolutely not. That's linear. If that was a straight line, I would say yes, that's exactly what you should do, right? Because that's the slope, and you substitute for a new x using the same slope. But here we are multiplying. Here we are multiplying by 135, by 135. We are not adding. So what are we multiplying for to get from 3 to 4? I multiply by 1755 divided by 6.5. So the rate of growth or the percent or the multiplier here is 2.6. So that would be wrong. I should get 5, and then you multiply 1755 by that value, and you get 47.39 if we use two decimal places, or 85 if you are using. So explain your reasoning. My reasoning here is that since this growth is exponential, then the rate of growth from one period to the other is the same. It's not the amount of growth, it's the rate of growth. And this rate is 2.7, meaning it's more than double. If it doubles, it's 13, and that's you get 17 something because it's 2.7. Okay? And I think that covers these types of questions. Next time, probably we are going to see how we are going to graph an exponential function. And then we are going to move to the logarithmic functions because the logarithms are the inverse of the exponential. And we will see then, now I can solve exponential equations. So instead of telling me y equals 3x minus 2 and 2y equals 5x plus 3, solve for x and y, no, I'm going to give you a function that is exponential on both sides. And we say, okay, how we are going to solve that? We need to apply the inverse, which is the logarithmic function, and then we'll do some logarithmic applications and learn how to graph it. And all these units are really straightforward, very simple if you keep track of very minor things. Once you understand them, it should be very easy for you to do. We'll look into that, and probably we'll see what we cover after that. So after the exponential and the logarithmic functions. Again, as usual, I remind you, if you have any questions or comments, to send me, to leave a comment in the comment section. I will get back to you as soon as I can. Otherwise, I wish you all the best and hope to see you soon.